chapter 34. So what I'd like to do right now is just jump into chapter 34 and finish the last part of the lecture. That's done, and then we can address questions. I do have an in-class problem. I have some special homework problems that I'd like to discuss with you. I'm going to save all of that to the end. Make sure we finish the lecture today. So what I'd like to begin with is my title of so far. Of course, we've got these three: time at a velocity, time at rest, root of 1 minus v squared over c squared. We notice that very often v over c is written as beta just for convenience. I will now use that when we measure length at a velocity is equal to length at rest times the root of 1 minus beta squared. And finally, we briefly mentioned, I believe, that mass at a velocity is equal to mass at rest divided by 1 minus beta squared. The square root sign like that. Oh, and by the way, sometimes 1 over 1 minus beta squared under the square root is sometimes called gamma. So sometimes we write this as m naught gamma. So these two symbols, you'll see them from time to time in various publications, as well as from time to time in my lectures, the beta and the gamma, but those are just little side notes to make the writing a little bit easier. I hope I made the point on Monday. I will remake the point today. It's extremely important that you remember what each time refers to. Don't simply read it as time at a velocity or time at rest. But keep in mind what we're talking about. For example, if I am the moving reference frame and you are the stationary reference frame, if I'm moving along at high speed, you observe my clock go slow. What you observe as the stationary person is you observe my clock go slow. So you're observing my time. You're observing my time. And this is the time that you would observe from your position. Likewise, if I'm traveling in this direction, you're observing me, my dimension and my meter stick shrink in this direction, you would observe a decrease in length, a smaller length from your stationary position, and this is lengths measured relative to you. And finally, mass and velocity. As I increase my speed, as I'm traveling at high speed, you would observe my mass increase. I would not observe that. You would. So each one of these is you looking from your stationary position into me, my reference frame is moving. Each one of these. This is what you measure when you observe my reference frame. That's the important part of special relativity, is to keep in mind what each one of these subscripted times, lengths, and mass represent. Also, these three equations are probably the best summary of special relativity, which deals with constant high speed only. Our next task is to begin to discuss the dynamics, relativistic dynamics, which is where you do start to talk about other possibilities. In this particular situation, let's start by talking about momentum and energy. Of course, as you recall from Physics 4, momentum is equal to P, and I'll put the vector hat on it just to remember that momentum is a vector, is given by mv, and the velocity is where you get the vector sense. Well, for us now, that means m naught gamma v. In Physics 4, we didn't even consider the fact that mass might change. The reason is because in classical times, and I mean from Newton forward for 200 years, nobody ever detected mass change. We thought mass was constant. Nothing went very fast. So, but now we realize that mass does have a variable property to it as the velocity gets quite large. This has an interesting consequence. You know what it is? You probably recall that the second law, Newton's second, F equals ma. F equals, but do you remember, I'm sure in Physics 4, you actually wrote it not as ma, but dp dt. dp dt. Of course, back then, when we thought of mass as constant, when we thought of momentum as just mv, you can bring the m out of the derivative, and dv dt is a, and that was all very simple and straightforward. But now we realize you can't just take mass out. It is not constant. Mass changes as velocity changes. Hence, therefore, force F is going to equal d by dt of, and let me write it out completely, m naught 1 over 1 minus beta squared times v, like that. And of course, beta has in it velocity, so that has to be there. So it's not the same thing. Now we realize that momentum, that Newton's second law has a different form. And that different form includes this term, which we used to simply ignore. That's going to come back in just a moment. Let me try to keep myself nicely organized today. Okay, so this color over here. In other words, from now on, this is how we're going to think of d of mv dt is going to be, of course, m dv dt plus v dm dt. So there's a second term in there, and this term does not vanish as it did in Physics 4. In Physics 4, the mdt, no change in m in time. So that term vanished. Now we realize that it doesn't. So that's going to affect everything we do. In particular, I'd like to take just a moment and look at energy now. We started with momentum. Let's talk about energy. We'll start with, of course, kinetic energy. That's the easy one. Energy, and I'll use kinetic energy. I'll use KE like that. As you recall, if we imagine that we have a particle, an object, anything, and it starts from rest and you apply a force to the object, then simply the kinetic energy, since you're starting from rest, the kinetic energy is going to equal the work done. So, KE equals work. And don't forget, we're assuming that you start with a zero velocity to be able to write it that simply like that. And you recall that that is, of course, the integral of F dot ds, where F represents the force that's applied and ds, S is the differential distance over which you apply the force. The dot product selects the component of force parallel to the displacement. Let us assume for just a moment that, kinetic energy initial was 0, and that F parallel to ds. So now we're assuming that we're going to just simply apply the force parallel. We're not going to worry about components at that point. So now, when we write that down, it is simply the kinetic energy is equal to the integral of F, but wait a minute, here's F over here. It's dp dt, so F is d of mv dt times ds. So we've gotten rid of the dot product by this assumption, and we've replaced force with its identification, which is essentially right here. Well, that's pretty handy because, of course, you know, don't you, what ds dt is. What is ds dt?
Distance over time.
ds dt is equal to, can you tell me? How about velocity? ds dt is velocity. The first time derivative of position is velocity. Hence, therefore, it gets really quite easy. Oops, not 2 pages. So what we have now is that the kinetic energy is equal to the integral of v of dmv, of course, from 0 to mv. Because remember, we assumed we started with 0 kinetic energy, so mv initial will be 0 and mv final will be mv. But don't forget, when we're putting in mv, we've got to put in this one here. So let's be quite specific about that. We put in, then, the integral of v times d of m naught v over 1 minus, let's just put beta squared under the square root, like this. And since now we have a derivative that really is related only to velocity, there's a velocity here, but within this differential, there's velocity here and there's velocity there. Therefore, now what's changing is not m times v, because our m has now been expressed as the initial mass, or the rest mass. Now we are integrating from 0 to v. We got rid of the m dependence by putting in the rest mass at that point. So what do? We're ready. We're ready to integrate. But what do? I'll tell you, integrate by parts. That's what we do. You look at that and you say, wait a minute, I'm not sure how to integrate something like that, right? Because you're not used to having this here. But as you recall, integration by parts will help a lot. So why don't you just take just a moment and integrate it by parts. And I'll remind you that the integral of x dy, if I write it down as the integrating by parts, how does it go? Remember? xy minus integral, that's right, y dx. Go ahead and integrate it. And see if you get what I'm about to write. So take just a moment and integrate it by parts, and then look at the board. Don't look at the board until you think you've got it right. So take this, integrate it by parts, and see if you get the answer that I'm about to write. But like I say, please don't look until you think you have it right. Probably stopped right here. Yeah. Because that's not a real easy integral to do. I have an in-class problem that helps you with that. So the next step of this integral is shown here, and I think it's written clearly enough that we don't have to read it. I'll pass it out. And it's an in-class problem, and I ask you to show something. If there's any questions after I'm done passing it out, please ask. what do we have? KE equals m naught v squared over 1 minus beta squared minus m naught times this integral, so it should be this term right here. What's that? Something strange has happened. Excuse me for a moment. In-class problem, so we just demonstrated that we have the kinetic energy is equal to minus m naught c squared times the root of 1 minus beta squared plus m naught c squared, like that. And oh, I see. Haven't finished this over here, have I? So let me see what I get here. I seem to have skipped a page in my notes. I don't know why I did that, but I seem to have. My next claim is that it becomes, oh, I think I see it. I think I see it. If we factor out, let me see, m naught v squared, 1 minus beta squared, plus m naught c squared root of 1 plus beta squared minus m naught c squared, like this. And then we try to combine, we endeavor to combine these two terms. We can do that by multiplying this term by 1 minus beta squared over 1 minus beta squared, both of them on the square root. So let's take a moment and look at this term here, m naught c squared root of 1 minus beta squared times 1 minus beta squared over 1 minus beta squared. That will put it over the same denominator. If I do this, what happens? I end up with m naught c squared times 1 minus b squared over c squared divided by root of 1 minus beta squared. And this is the missing page of notes. So watch my algebra closely. And when I multiply that thing out, let's see, what do I get? I get on top, we're now just concentrating just on this term right here. So, what do I get? M naught c squared root of 1 minus beta squared becomes m naught c squared minus m naught v squared over 1 minus beta squared under the square root. Now insert that right here. So kinetic energy becomes m naught v squared 1 minus beta squared plus this term plus this term m naught c squared root of 1 minus beta squared minus m naught v squared over 1 minus beta squared minus this term, which is minus m naught c squared. Now let's check and see if I did that correctly. What I just did was to put this term over that denominator using this. That done, I get m naught c squared times 1 minus beta squared over that denominator. Then I stuck that right back in here, so I've got this term at the beginning. Let me just check. I've got this term at the beginning, I've got this term at the end, and I've got this thing in the middle. Looks good to me. Does it look good to you? Great, I'm happy, because, of course, we see m naught v squared over 1 minus beta. We see minus m naught v squared over 1. It's gone. Great, fantastic. We did what we wanted to do. We got rid of this ugly, nasty thing. And so what do we have left? We have left that kinetic energy. Is it? How come you're not excited? Isn't this fun? Aren't we having fun? Is equal to m naught c squared over 1 minus beta squared square root minus m naught c squared. But of course, we recognize this creature, use a different color, blue. We recognize this creature right here as simply m, not m naught, but m. So, kinetic energy is equal to mc squared minus m naught c squared. That's how Einstein made the discovery, ladies and gentlemen. E equals mc squared. Or a better way of writing it, I like it better anyway, is to write that mc squared is equal to m naught c squared plus kinetic energy. And then we realize that this term, mc squared, is total energy. Energy total equals mc squared. Something we call rest energy is equal to m naught c squared. So the total energy of a particle is its rest mass energy plus its kinetic energy. E equals mc squared. Mass and energy are equivalent to each other. And the way we describe that is to call this thing the rest energy. So an object of mass m naught sitting stationary possesses energy. I like to think of it as a form of potential energy. Rest mass energy is a form of potential energy. So on my paper I wrote E equals mc squared exclamation point. So the old-fashioned conservation of mass and conservation of energies, which I think is a law that they actually still teach in chemistry, don't they?
Yeah.
Yes. It ain't so. There is not two separate laws. It's conservation of mass energy. Mass and energy are two different manifestations of the same thing. In a reaction of any kind, chemical reaction or any kind, the only thing that remains constant is the total of mass plus energy. You don't have a conservation of mass and a conservation of energy. It's a single law.
We could transfer some mass to energy and/or energy to mass.
Absolutely. Absolutely, and this was an amazing discovery. And I think I might be aware, I might be cognizant of that dubious look some of you are giving me.
Under what conditions would that happen?
First off, yes, that's a key question he asks right there. And first off, you have to get a feeling for what you're talking about. Let me give you an example. 1 kilogram of mass, which is just a little bit less than the mass of your book. how much energy is there? Well, it's really easy. How much rest mass energy is there? It's simply m naught c squared, 1 kg of mass times 3 times 10 to the 8 meters per second squared is 9 times 10 to the 16 joules. Sounds big, doesn't it? It is big. I thought of an interesting way of sort of getting an idea of how big this amount of energy is. And I asked myself this question. This amount of energy, how far above the Earth's surface will it lift a given mass? I thought to myself, that might be an interesting way of determining it. So I thought, well, let's take an unknown mass to the moon. Let's find out how much work is required to move an unknown mass to the moon and then calculate how much mass this amount of energy would move to the moon. So how would you do that? You got to think back, of course, to your Physics 4 days. But if you were back at Physics 4 and you wanted to lift a mass from the surface of the Earth to the moon's orbit, as far out as the moon, what would you do?
Force times distance.
So work equals, of course, the integral of F dot ds. And for us, we're going to assume we got a rocket, so the force is parallel to the displacement, so we don't have to worry about the dot product. What would you put in for force?
Force of gravity.
Yes. The integral of G, capital M with a circle and an X in it, small m over R squared dr. Now, S has become R because I'm measuring radii. So there's the force of gravity. Since you're moving to the moon, the force of gravity is not constant. We only use F equals mg when you're sticking close to the surface of the Earth. So what do we put in here? G, of course, is the universal gravitational constant. It is a constant. This m is what? When it has a circle with an X in it, what is it? That's the Earth's mass. This is the radius to which we are moving. What is this little mass? That's the unknown mass that we're lifting. That's the one that we're looking for. And of course, so we can pull all of this stuff out front. Now go ahead, your question.
Technically, you're missing a part.
Technically, I'm missing a part, what?
Because the moon has mass too.
Okay, technically we're missing a part. He's talking about the fact that when you get really close to the moon is going to attract a little bit, but we're just making an estimate. We're not being technical right now. But you are correct, absolutely. If we were, if we were JPL, we'd take that into account. You can do that when you transfer to Caltech. And that's your ambition, every one of you, right, to go to Caltech. Second best university in the world. So, what we have then is G, M, integral from 0 to R. Here's another technical point if you notice it. I'm not going to say it right off. dr over R squared. Okay? That's all we have to do. We assume that we do the appropriate amount of work. Let us assume that we do this amount of work, so we've got a number for W. We've got a number for all of this. So what we have then is that work divided by G, M, must equal the integral dr over R squared, like this. And that's the radius of the moon's orbit. So when we're done, really, the unknown mass goes here and the integral goes down there. So the unknown mass that we are lifting is equal to the work that we do divided by the universal gravitational constant, the mass of the Earth, and the integral from 0 to the radius of the moon's orbit of dr over R squared, which of course is simple. So we've got everything we need, except, of course, putting in the numbers with the correct units. When I was done with this calculation, and I challenge you to finish the actual calculation, I don't want to look up all the numbers right now, but I got about 1 million tons. What I just said, ladies and gentlemen, is the amount of energy locked up in your book as mass energy is enough energy to lift 1 million tons to the moon. That's a hell of a lot of energy, isn't it? That's true. That's what mass energy is all about. Now I can get around to your original point, which was a good point. And basically, I think if I understood what you were saying, basically it was like, oh yeah, how come we never saw this before in chemistry? When you use conservation of mass in chemistry and you use conservation of energy in chemistry, it works. Why? It's because the kind of reactions that you're doing aren't anything like this sort of energy, are they? They're so puny, you never notice the missing mass. I think we've got another example problem before I go on here. Yes, look at this. 1 kilogram of dynamite liberates about 5.4 times 10 to the 6 joules of energy. It does it by losing mass. When you detonate a kilogram of dynamite, it converts some of its mass into energy. Let's figure out how much mass is converted into energy, because that's a pretty energetic chemical reaction, isn't it? A kilogram of dynamite is a pretty energetic chemical reaction. So, let's put on the board here what's going on. That is 1 kg of dynamite. .4 times 10 to the 6 joules of energy are released. So we ask, m naught c squared equals 5.4 10 to the 6 joules. How much mass disappeared in this reaction? So m naught is going to be 5.4 10 to the 6, what are the units on joules? kg, meters squared per second squared, divided by c squared, which is 9, 10 to the 16 meters squared per second squared. Nicely, the units work out beautifully. And of course, we have 9 into 5.4, which is 0.6. 10 to the 16 downstairs, 10 to the 6 upstairs, so that's times 10 to the minus 10 kgs, or about 6 times 10 to the minus 11 kgs. I defy you to measure that after the explosion. Detonate a kilogram of dynamite and then go find that you have this much less dynamite particles left. Or, the way a lot of people say it is, this amount of mass is very hard to notice, whereas the energy release is hard to ignore. Yes?
So, is this implying that all the energy released is because we're doing mass to energy?
Yes. Did you hear what he said? He said, does this imply that all energy release is a conversion of mass into energy? And the answer is yes. It's just that the kinds of energy releases we are used to represent such a puny loss of mass that we never noticed it before.
So it always is.
It always is. Anytime you have any energy release, it was at the expense of mass someplace. Just don't forget that we deal with puny amounts of energy. This is considered a puny amount of energy compared to that one over there, huh?
So that's
Correct.
not just like nuclear energy, that's any
Nuclear energies are about 1,000,000 times more energetic. A nuclear reaction is about 1,000,000 times more energetic than a chemical reaction. nuclear, about 1 million times more energetic than chemical. And that's why when you do nuclear reactions, you actually do notice mass missing. If you do nuclear reactions, and you can actually measure the missing mass, but not in chemical reactions. It's so small, it's almost beyond our ability to do experimentation. Okay, now I have another very interesting question for you, and that is what happens when v is small. We've been thinking about things relativistically. We always think about things where velocities are high. What happens when the velocity is small? This is kind of an interesting consequence, and I want to spend some time discussing it after we have noted the consequences. What if v is small? What happens then? Well, it's kind of interesting. You already know that kinetic energy, relativistically speaking, is total energy, mc squared, minus rest energy, m naught c squared. Which, of course, could be written as m naught c squared times gamma minus 1. Let's fill in for gamma a little bit at least. M naught c squared 1 over 1 minus beta squared under the square root minus 1. And the reason that we do that is because when v is small, of course, beta is much, much less than 1. It is also small. So we're talking about small, shall we call them ordinary velocities, velocities of spacecraft and things like that, maybe asteroids and things like that. What goes on? Well, the neat thing is we can evaluate this quite nicely by simply doing an expansion. All we have to do is expand this term. That is 1 minus beta squared to the minus 1/2 power. And as you recall, the binomial expansion 1 minus x to the n is equal to, well, 1 plus nx plus, and it never ends. There's a long, long set of terms. But if x is small, the next term is x squared, which is trivial. So we're going to approximate it by keeping just 1 plus nx. The rest of it is real but trivial, because every subsequent term is a higher power on x, and we've already argued that x is small. That is beta. So, oops, I don't have that right. Ladies and gentlemen, I don't have that right. Please fix that on your notes. So, I can say then that the above expression, just ditto marks if you will, is equal to 1 plus n x and I get a double negative. I get a negative because that's a negative 1/2 for n, and I get a negative because plus negative beta squared. So this simply becomes then 1 plus beta squared is our what do we do? See, I told you. Plus 1/2 beta squared. And we can simply insert that right here. So we get then that the kinetic energy is equal to m naught c squared times this creature, which is 1 plus 1/2 beta squared minus 1 but we got a 1 minus 1, that's nice. So we end up with, then our new kinetic energy, Ke, equals m naught c squared times 1/2, write that a little nicer, times 1/2 v squared over c squared. Lo and behold, we get 1/2 m naught v squared. Have you ever seen that before? Never. What a surprise. I've never seen that before. It is not a coincidence that the relativistic formula reduces to the classical formula when you're dealing in classical velocities. It's not a coincidence. As you know, for hundreds of years after Newton's time, people tested classical formulas and they worked beautifully. You tested classical formulas in your Physics 4 and they worked beautifully. A requirement on this new study of relativity, a requirement is no matter what your conclusion is in relativity, it must reduce to a classical conclusion under these conditions. If beta is very small, implying if velocities are quite small, you better get classical results. Why? Because we've been getting those in experiments forever. We know that the classical situation works beautifully in classical experiments. So, one of the tests you give to every new relativity idea, one of the tests you give it is, okay, this is a conclusion of what's happening in a relativistic situation. What happens if we slow everything down to classical speeds? You better get the classical result, just like this did. Okay. So one of the things I like to do, I like to think of it like this. Here's classical mechanics, just call it CM, classical mechanics, or Newtonian mechanics. Relativistic mechanics is like this. Relativistic mechanics must completely encompass classical mechanics and then give you further solutions beyond what classical can do. Classical can only handle low velocity. Relativity should be able to handle both. If relativity is correct, then it must be able to handle high velocities and low velocities. So, relativistic mechanics, RM, must completely encompass classical mechanics. That's a requirement. Pretty neat though, huh?
Yeah.
I can see how excited you all are. Let's go out and have a carbonated beverage.
Okay.
Awesome.
All right. So does that takes care of this page.
Did you say quantum mechanics should be all by itself? Is it circular?
Unfortunately, it is. You know what? Quantum mechanics would look sort of like this. Look. There's quantum mechanics.
That's fine.
Quantum mechanics does seem to do a great job of taking into account classical. Both quantum mechanics and relativistic mechanics encompass classical, but they don't talk to each other. Quantum does not talk to relativity, relativity does not talk to quantum, but they both talk to classical mechanics. Isn't it funny? It's a little bit like the zeroth law of thermodynamics. That is, remember we said that if object A is in thermodynamic equilibrium with object B, and object B is in thermodynamic equilibrium with object C, then A is in equilibrium with C, right?
Yeah.
Well, here we've got A and B, we've got A and C, but we haven't yet got C and A together. C and B together. We haven't got those other two together anyway. It's like we haven't finished the zeroth law of thermodynamics when it comes to the different mechanics. Now, you had a question, Christine?
I was going to say, why not?
Because you haven't finished yet. You must finish your PhD and then you can do it. I guarantee you, when you have finished this, you will get a Nobel Prize. And life will be wonderful. So much better than winning the lottery. Everybody goes and plays the lottery, right? Chump change. Chump change compared to winning the Nobel Prize. The nice thing is the lottery is pure random, but the Nobel Prize has to do with how much you work. So you can win a Nobel Prize. You can set out to do it and win. All I ask is when you step up to the microphone to receive your prize, you say, I owe it all to Doria. Why not? We're not done yet, that's why not. Okay, I got a new topic, if we're ready to go for the new topic. One last page. 2 pages to go. We only got 2 pages to go, we got almost enough time to do it. All right, any questions about what we've done so far before we get on to the next bit here? The next bit's really neat too, you're gonna like this, this is fun. Yes? Because what I'm talking about is the dynamite's just sitting there, and then some of that rest mass is, a small amount of that rest mass is converted. So that's why I chose it.
But only the you didn't add the KP, the kinetic energy to one side and the other. You said the rest mass was equal to the square.
Because you need this rest mass here?
No, above the first line.
Above it, up here?
Yes.
Because what I'm saying is how much energy is sitting there in that book right now. That book is sitting there stationary. Okay? Subtle, but the type of question you need to ask yourself every single time you do this. Which M do I put in and why? So, subtle question he asked, but an important one for you to ask of yourself each time. All right, I want to go on now to the new and final topic. Final topic? No, it's not. The new and the second to the final topic today. That is, can massless particles exist? You said yes. How do you know? Because somebody told you? Nah, we're physicists. We're going to check it out. We don't care what anybody else says. Even Einstein, we're going to check it out. Can massless particles exist? Maybe. Let's check it out. Here's how we do it. Let's start by describing the energy of a massless particle. So the energy of a massless particle, of course, is mc squared. M naught c squared over 1 minus v squared over c squared under the square root. And the momentum of a particle, P, the momentum of a particle is, of course, mv, M naught v, over 1 minus v squared over c squared. Okay, there's the mass and, there's the energy and the momentum of a particle, Of course, you notice that if m naught is 0, if m naught equals 0 and v is less than c, then E equals P equals 0. Right? If m naught is 0 and v is less than c, then this is some real number, and that's 0. Likewise. Well, a particle with no energy and no momentum is no particle at all. But, put a big but on the board. But, if m naught equals 0 and v equals c, then E equals 0 over 0 and P equals 0 over 0. And what do the mathematicians, careful, what word do the mathematicians use? Indeterminate. That says E could be real, and P could be some real finite value. Hence, therefore, we conclude that if massless particles exist, they can only exist at the speed of light. If they exist below the speed of light, there's no energy, no momentum, you really don't have a particle. If they exist at the speed of light, then there's a chance that you could have an energy and a momentum. And by the way, a subtle little point for your future lectures. You see how I did this? E equals P equals 0. Do you know why I did not write E equals P equals 0 over 0? I did not write this. I'm going to put a big X through it. For a very specific reason. That's correct. They might not be the same. They are both indeterminate, but they are probably different. They're indeterminate, but they're probably different. That's why. Yes, good. Good point. Where am I? So, we have concluded that there's no way to get rid of them. We haven't concluded that we haven't proven that massless particles exist, but we have found no obvious way of saying they do not exist. So, if this, then this, if that, then that, so maybe, that's what I wrote on my paper. So maybe. If and only if, so you write that down, don't you? If and only if I, F, F, B equals C. That's the only way massless particles can exist at the speed of light. I suspect you know which particle I'm talking about, but I haven't given it a name, and I shouldn't give it a name for about 2 more lectures, but I suspect you know which particle I'm talking about. Which particle am I talking about?
Photon.
That's correct, the photon. And the photon, all I can say to you is that when photons are cruising around, they exist. And if you stop them, they don't exist anymore. You slow a photon down below the speed of light and they don't exist anymore. But anyway, I'm not supposed to say that, so you know that. Now, here's something else, another interesting thing to notice. What happens with E squared? Well, that's interesting because E squared is just the square of this thing. How come I wrote it as a square over here? Who cares? It is, of course, equal to m naught squared c to the 4th over 1 minus v squared over c squared. And what about p squared? P squared equals this creature here squared, which is m naught squared v squared over the same thing, 1 minus v squared over c squared, like this. Well, that's lovely. But who cares? Well, notice that, of course, we have different units, don't we? You know what I just wrote on my paper here? I said, E squared and P squared, apples and oranges, right? Isn't that classical statement? All of the Algebra 1 teachers say you can't add apples and oranges, right? So that's what we have. We have apples and oranges. How do you know that? Everything else, yes, you're absolutely right. Everything else is the same except we've got c to the 4th, so we're going to have meters to the 4th over seconds to the 4th, and here we've got meters squared over seconds squared. They're not the same units, you can't put them together. But what if I just, for that reason alone, I write down p squared c squared, which is m naught squared v squared c squared over 1 minus v squared over c squared. Now we have the same units. We got the same units, we got apples and apples, let's add the apples together. Okay? You're just wondering, why in the world do that? Just because it's fun. You guys look a little bored. We want to have some fun. E squared plus p squared c squared becomes m naught squared c to the 4th over 1 minus v squared over c squared plus m naught squared v squared c squared over 1 minus v squared over c squared. Isn't that cool?
Just so.
I don't know how cool it is.
Maybe.
But I have this idea. Why don't we factor out? Look, we can factor out m naught squared c to the 4th. Can't we? We can. Watch. I can do it. I can do it for the fun of it. M naught squared c to the 4th times 1 plus v squared over c squared divided by 1 minus
That's what I'm asking.
Oh, why didn't you notice this?
I don't know. I don't
You
even
should
know
have
what I'm
noticed
doing
this,
here.
ladies and gentlemen. Everybody wanted to do this, not that. Everybody wanted to do this. You didn't stop me. And that's what you wanted to do, don't you remember?
Sure.
Why?
Totally.
Because it's more fun than what we were about to do.
Totally.
Now we're having fun. Oh, I realize now, at first you weren't having fun, but I can see why. And lo and behold, what do we have? We've got the same thing, top and bottom, it goes away. Aha! There's where the fun is. Canceling. Wasn't that the best part of fractions?
Yes.
Canceling.
That's so satisfying.
All right. So finally, you get around to what you want to get around to. E squared minus P squared C squared equals M naught squared C to the fourth power. But we'll rearrange that for a more convenient writing over here. I'm going to get away from the board where I make a mistake because it's all the board's fault.
Totally.
So we come over here and we write down E squared equals, and then let's look over there. E squared is M naught squared C to the fourth plus P squared C squared. There's the plus sign. M naught squared C to the fourth plus P squared C squared, like that. Then take the square root on both sides. E equals M naught squared C to the fourth plus P squared C squared. Under the square root like that. Aha! We now have a relationship, shall I call it, relativistic relationship between energy and momentum. The energy of a particle and the momentum of the particle. And not surprisingly, it involves the rest mass energy. But even more interesting, are you ready for something more interesting? I know you are. What if there were a massless particle? In a massless particle, then of course this term is gone and we have E equals PC. So in terms of a massless particle, you have a very interesting, odd relationship between energy and momentum. In a massless particle, the energy is the momentum times the speed of light. If it's not a massless particle, then the energy must include the rest mass energy. No rest mass energy, and it gets more simple than that. All right. This is so exciting. Oh, drat. I already did this problem for you, but I'm going to make it a homework problem anyway. I have two homework problems. I'm going to pass them around. You guys be so kind.
Underlined.
Give a copy to everybody, please. And I'll wait just a second while they're doing that, and I'll talk to you about the first one that says homework and kinetic energy is equal to the integral from 0 to mv of v dmv. We've actually already done that. I did that for you, and that just shows you what a great human being I actually am.
Just get back to 101, and then brings up the same process.
So you no longer have any doubt in your mind.